Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today what we are going to learn is all about lesson 11, which is the electronic structure and periodicity. In this lesson, what we are going to discuss is basically various trends, or in other words, patterns that you would see in the periodic table of elements. When we talk about the periodic table of elements, this is something that you would normally would have imagined. And that makes sense, even though you probably have not taken any chemical or chemistry lessons, you are probably familiar with these table of elements along with the various names that may not be familiar with you. But when we actually created the table of elements, the scientists back in the 1800s had a discussion on how to effectively tabulate all the elements that we have discovered in the earth. It was not until Dmitry Mendeleev, the one that created this table of elements that we have now, that he grouped these table of elements very wisely, because not only are we able to see the various elements that we have now, but he was able to create a table in such a way that we can actually see what we call a pattern. So we call it periodic table of elements because by looking at these, we can actually see various beautiful patterns that the elements exhibit. And that's what we are going to learn today. Learn some of the patterns that is available by just looking at the periodic table of elements. But first, let's learn more about how Mendeleev grouped these elements. The first way that he grouped them is via what we call a group or family. When we talk about group or family of elements, it's basically the column. So right here, this group number 1 right here, or you can think of it as column number 1, is basically the set of elements that are in a column together. So for example, the hydrogen, lithium, sodium are all in one group, while the one that are in rows, for example right here, are what we call periods. So Mendeleev created or tabulated all the elements in this way. And one of the important things to note about why they were grouped this way is because all the elements in the group, helium or hydrogen, lithium, sodium, are actually exhibiting very similar chemical and physical properties. So hydrogen, lithium, sodium, all of these in group number 1 are all actually exhibiting very similar chemical and physical properties in such a way that when Mendeleev created this, a lot of the elements, especially around this area, are actually still missing. We have not discovered them. But because the way that Mendeleev created the groupings of the element, we can actually, or he actually predicted the properties of the missing elements in such a way that when we discovered them finally and look at the notes of the properties that Mendeleev tried to assume, the properties that he assumed and the properties that the elements we discover are actually matching. And that is because, again, the elements that fall within the group are exhibiting very similar properties. And back then, we do not actually understand why. Why did these elements within the group are exhibiting very similar chemical and physical properties? It was not until very recently that we discovered the reason for that. And that is because of the valence shell. Remember from our discussion long time ago, we talk about a valence electron. Valence electron is basically the electron that you will find on the outermost shell of an element. Remember the Bohr's model of an atom? When we talk about the Bohr's model of an atom, you have your nucleus right here. So in here, you have your neutrons and your protons. And around your nucleus, you usually have your electrons. And usually the electrons right here, so we'll have are in a shell. So you have, for example, right here, so you can think of this as your electron. And what we talk about then is, as we actually go within this group right here, the number of shell is actually increasing. But what is interesting is that this group specifically what we call the group A. Group A composes of group 1, group 2, group 13, which we also actually what we also call group 3, group 4, group 5, 6, 7, and 8 are all what we call group A, and we call this representative elements. That is because depending on their group number, this actually tells you how many valence electron is on their valence shell. Again, I hope you remember what valence is. Valence is the outermost shell of the electron. The reason that these elements that within the group exhibit a very similar chemical and physical properties is because they have the same number of valence electron. As for example, right here you have your hydrogen. We know that in hydrogen, it's basically composed of one proton and one electron. So this has your proton right here, and it has one electron in its outermost shell. And the next one is lithium. As for lithium, we know that lithium actually is composed of 3 protons, so you have your 3 number there. That atomic number is number 3 is telling you how many protons and how many electrons you have. So this lithium right here has 3 protons and has 3 electrons, and if we actually draw that using Bohr's model, we would know that lithium would have its first shell filled. And I hope you remember that when we are drawing the Bohr's model, the first valence or the first shell of an element can only have 2 electrons. So that's 1 electron, that's 2 electron, and then it has to move on the next electron. And as you can see, if lithium has only 3 electrons in its outermost shell, this is its outermost shell right now, which is what we call again the valence shell, it will only have 1 electron in its outermost shell. And if you actually keep looking, the same is true even for sodium. If you draw sodium using the Bohr's model, you would have something like this, wherein it has 2 electrons, and then it will have its next shell, and for the next shell it can contain about 8 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8, and then it will have to have its third shell with 1 electron. And as you can see right here in their outermost shell, this is helium right, or hydrogen right here, they have 1 electron in their outermost shell. And if you keep doing that on all of these elements, for beryllium, for group number 2, they would have 2 electrons in their outermost shell. As for group number 13, the reason that we call it also group 3 is because the elements right here has 3 electrons in its outermost shell. Group 4 has 4 electrons in its outermost shell, and 5, 5, 6, 6, 7, 7, and 8, 8. And 8 here, right here, that's why we call them noble gases, is because they're very stable. Because as we have discussed long time ago, a shell can only contain 8 electrons, except for the first shell. So the first shell right here, this is your first shell, this is your second shell, 3, 4, 5, etc. The shells within 2, 3, 4 and higher number can have 8 electrons, right? So the elements that falls within group number 8 has their shell completely filled, which makes them noble gases, which makes them very, very stable. So helium, neon, argon, xenon, etc. are all actually very stable elements. They're not very reactive. And this group again is what we call group A, because the representative elements, because the representative number or the representative group number, group 1, group 2, group 3, 4, etc. is actually telling you how many valence electron is there, or how many electrons are present in their valence shell. And then we have another group called group B, which are basically the transition metals and the inner transition metals. Group B is basically this part right here. These are your metals. that we commonly know. You have your nickel, copper, zinc, gold, silver, etc. Transition metals is what's connecting the left group A to the right group A. And then you have your inner transitional metals, which includes the lanthanoids and the actinoids, which are the elements right here. So that is how you would, this is how Mendeleev created the periodic table of elements. Now that we know uh, how the elements are tabulated, uh, let's learn about some of the trends that we can actually see on the periodic table of elements. But before that, let's talk about the periodic number. Periodic number is basically the highest energy level that the electrons or the valence electron occupies. The energy level that we're talking about here is the main energy level from our discussion in lesson 10. The main energy level, if you are writing your electron configuration, are the numbers in front. So these 2, 3, 3, 4 are the main energy level. So the periodic number is basically the last main energy level wherein the last electrons are situated for that element. So if you write the electron configuration of potassium, which has 19 electrons, you would write 1s2, 2s2 until such you were able to fill all the electrons in its electron configuration and then writing the last one. Potassium, you know, is in group A, right? In group A, specifically group number 1. Group 1 has one valence electron, and as you can see right here, this electron right here is the last electron in its valence shell, and this electron is found at the fourth main energy level, number 4. So the period number 4, potassium, is actually number 4. So simply said, the periodic number is basically the main energy level wherein the last electrons are found. Okay. So calcium is in group 2A, so it's in group A, group number 2. So since it's in group number 2, we know it should have 2 valence electron, 2 electrons in its outermost shell. And if you write the electron configuration of a calcium, which has a 20 20 as its atomic number, which tells you on its ground state it has 20 electrons, you would have this electron configuration right here, and you would know that it will ended up with 4s2, which means that the periodic number for calcium is period number 4. So that's what basically periodic number is. Okay, simple enough. Now let's go and discuss some various trends that we can see in the periodic table of elements, beginning in what we call the atomic radii. When we talk about atomic radii, you can just basically think of it as the size of the electron. If you imagine the electron, you can think of it as a sphere. And radii is basically the size of the half of the diameter of the sphere. So atomic radii, when we talk about atomic radii, this is basically the size of the electron. And one of the first trends that we will see in the periodic table of elements is that if we go downward, so this is your periodic table of elements, but they are written in terms of the atomic radii. By going downward, the periodic table of elements, and not only downward, going from right to left, the atomic radii is actually increasing, meaning the size of the electron is increasing. And that actually makes sense, because if we draw these electrons using the Bohr's model, we know that, for example, let's start with group 1A again. You have your hydrogen. Hydrogen only has one proton and one electron. So if we draw it using the Bohr's model, we would know it has one electron. And then we will have lithium next. We know that for lithium, it has how many electrons? It has 3 electrons. So we would start with the first shell, which can contain 2 electrons, and then it will have its next shell, which it will contain its last electron. And then going even lower, you would have your sodium next, which will have about 11 electrons. So you would have your sodium right here. Let's go a little more lower. So you have your sodium. So it will fill its first shell, and then it will fill its next shell with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So that's 10. And then it will have its third shell, wherein its last electron will be found. And what you notice is they're increasing in size. So the periodic table is actually showing you the size of the electron by going downward the periodic table, and by going from right to left, the atomic size is increasing. Moreover, if you go on the opposite side, proceeding from the right going to the left, the atomic size decreases. So if you see right here, if you start at potassium right here and go towards this size, you would see that the size of the electrons are actually decreasing. Of course, there's what do you call this, an exemption. That is when you arrive at the noble gases. The noble gases are very stable. That's why their sizes are much bigger. But that's the first thing that I want you guys to remember. The first strand is the atomic radii. As you go downward or go from right to left, the atomic radii is increasing. And this makes sense because if you remember, the only differences between, for example, an hydrogen and helium is the number of protons. Hydrogen has 1 proton and helium has 2 protons. Lithium has 3 protons, and the next one, beryllium, has 4 protons. Okay, so what is happening is because the protons are increasing, the nucleus is increasing its in size, and as you can see, it's becoming more has more positive in its nucleus because protons are found in its nucleus. What is happening is, as you increase the number of protons in the nucleus, the electrons get feels to be attracted more to the nucleus. And when the electrons feel more attracted to the nucleus, you can think of it as they want to be closer to the nucleus. And since we are increasing the number of protons as we go from left to right, the number of protons is increasing, the electrons feel more attracted to the nucleus. That's why they are shrinking. The electrons wants to get closer to the nucleus. Okay, and that's what we call the nuclear charge. The nuclear charge is the strength of attraction between the nucleus and the electrons. By increasing the number of protons, we are increasing the nuclear charge, meaning the electrons that surround the core of your element, the core of your element, gets more attracted. So when the electrons gets more attracted, they kind of like shrink because they want to get closer to your nucleus. And there are various atomic radii. We have covalent radii and metallic radii. So metallic radii are basically the radius of metallic elements, and covalent are those that are non-metallic. Okay, so this is the first trend that I want you guys to remember. It's the size of the atomic radii. As you go down and go from right to left, the size of the atom is basically increasing. And the reason for that is because when you go from left to right, the nuclear charge is increasing because electrons tend to feel more attracted towards their nucleus as you go from left to right. And that is because we are increasing the number of protons from left to right. Okay, so I hope that is clear. So that is our first periodic variation or periodic trend or our first periodic pattern. Our next periodic pattern is a little bit different. It's called the ionic radius. Ionic radius is different from atomic radius because ionic radius, when we talk about it, we are actually talking about the radius of the cations and the radius of an ion. Basically, this is the radius of an ionic compound. Okay. So if we look at the most common ionic compound that we have, it's sodium chloride. We know that in a ionic compound, we should have a metal and we should have a non-metal. And what happens is that the metal will readily donate its electron to the non-metal. So it has, what happens is that our metal becomes more positive, making it a cation, and our non-metal becomes more negative, making it an anion because it gains an electron. Okay, so how do the radius of these ionic compounds change? Well, the reason for that is because electrons repel each other. When an atom gains an electron and it becomes an anion, remember, an ion, it gains an electron, they become more negative. Because they gain an electron and because electrons repel each other, their size basically increases. So this is a neutral chlorine, and when it becomes a anion chlorine, the size increases, as you can see right here. Again, the reason for that is because electrons like to repel each other. So by gaining electron, it increases its size. And also, when an atom donates its electron, or basically loses an electron and become a cation, so this is for sodium. A normal sodium has this size right here, but when it becomes an Na plus or an Na cation, sodium cation, its size decreases. The reason being it donated its electron. Okay, so just simple as that. So that is for the ionic radius trend. Also, ions with the same electronic configuration. So for example, all the particles here has this same electronic configuration. The radii would actually decrease as their atomic number increases. So, but that's not important. But for now, what I want you guys to remember is this pattern right here. When an atom gains an electron and becomes an anion, their size increases, their radius increases. And if an atom donates its electron, making it more positive, making it a cation, what happens is that they loses their size, or they become much more smaller. So that is for the ionic radius. So we've discussed two patterns so far, atomic radius and ionic radius. Next, let's talk about another pattern called the ionization energy. Ionization energy is basically the energy in terms of kilojoules per mole that is required for an atom to remove its electron or donate its electron. How much energy do I need in order for an atom to donate its electron? And the trend for that, if you look at here, is we have a trend that is like this. So the ionization energy increases going this way. So as we go from left to right, the ionization energy increases, and as we go from bottom to top, the ionization energy increases. So let's just remove this and just imagine that the ionization energy is increasing towards this direction. So there is an increase towards this side. Okay, so left to right increase, down up increase. So why is that? Well, the electrons wants to remove, or the electron that is being removed from the atom is always going to be the electron on its outermost shell. So we're going back to the idea of the valence electron. Okay, so what happens is that maybe let's look at the example right here. So let's look at the francium right here. Francium is very, very, very big. So remember, as we go downward for the atomic radius, our atoms gets bigger. And as our francium gets so much bigger, it will have usually we have your it will so this is usually helium, lithium. It will have your sodium, a potassium. You would have your Rb, and then cesium, and finally it's valence electron. So the valence electron of francium is actually around this area, and as you can see here, there's already so much shell before going through its last shell. What is happening is the concept that the electromagnetic force drops off with the distance, meaning the farther the electron is from the nucleus, the more the electron is readily can be easily removed. Okay, and so compare that with helium. Helium has what? Has only 2 electrons, and it's all found in its first valence shell. So they are very much closer to the core or to the nucleus of helium. So it takes more energy for the electron of helium to be removed. It takes more energy for helium to be ionized. So when we ionize something, we are removing or gaining an electron. And for francium, since its last electron, again, the electron that should be removed is the electron from its outermost shell. And since francium is really, really big, it has all of these shells right here are filled with electrons, and then its last electron is in this shell right here. And since it is so much farther from the nucleus of francium, this electron can be easily donated compared to helium. So the trend of the ionization energy is going towards this way. And like the one that I've mentioned here, the ionization trend is actually precisely the opposite direction. The direction of the atomic radius, if we go down, it increases. And if we go this way, it increases. So for ionization, the trend is towards this way. But for atomic radii, this is for the radius, the trend is going this way. So the radius increases as you go down and from right to left, but the ionization energy is going from up to left to right and down to up. So remember again, the concept is because the farther the electron from the nucleus, the more readily this electron will be donated or will be removed, which means the smaller the electron, the more difficult the smaller the atom, the more difficult it is for the electron to be removed. And we know that as we go towards this way, electron tends to be much more smaller. Okay, so I hope that makes sense. So that is ionization energy. Another periodic trend that we are going to discuss is called the electron affinity and electron negativity. Electron affinity is basically the opposite of ionization energy. If ionization energy is how much energy the atom needs in order to remove its electron, electron affinity is basically telling you how much the atom wants to keep that electron. And electron negativity or electron affinity has a trend that is also similar with the ionization energy. The ionization energy increases towards this way. So the higher the ionization energy, right, the higher the ionization energy, the more difficult it is for the electron to remove, or the more difficult it is for the atom to remove its electron, which means the more the affinity it has for that electron, the more that it wants to keep that electron. So they have the same trend. It's going towards this way. And also for electronegativity, which is the ability of the atom to hold onto the electron. So electron affinity and electron negativity is you may get confused because they're very much the same, but electron affinity is basically gaining an electron, opposite of ionization energy, which is losing an electron. Electronegativity is how much it wants to hold onto that electron, and it also has a direction going towards this way. So if you look at here, fluorine actually has the highest electron affinity and electron negativity. First, because if it gains an electron, it will have a full shell. Fluorine has 7 electrons because it's in group G7, group A7, right? It's in column 7. It has 7 electrons in its outermost shell. And remember, how many electrons do we want on each of the shell? We need 8, meaning it only needs one more electron for it to be stabilized. So it really wants that one electron. It has high affinity to electron. As opposed to, if we look here, the elements right here actually wants to readily donate their electron. The reason for that, remember, for our group 1A, they have 1 electron on their outermost shell. So let's take sodium or lithium, for example. Lithium has its first shell filled, and then it has its second shell with just 1 electron. And if lithium actually donated this electron, what you would notice, it's actually very stable right now. This shell right here is satisfied. The same is true for sodium. So we have our sodium with our 2 electrons, and its second shell with 8 electrons, 3, 4, 5, 6, 7, 8, and then it has its third shell with 1 electron. When sodium donates this electron right here, now what you notice is that all of its shell is fully filled. It makes it more stable. That's why sodium is so ready to become a cation in our NaCl. It's so ready to donate its electron to Cl, because if you look right here, Cl is what? Cl has 7 electrons in its outermost shell, meaning by gaining 1 electron, that shell becomes fully filled. Okay? So that's what makes ionization very, very strong, a very, very strong compound, a very strong combination of 2 elements. And going back, fluorine has highest electron negativity. It's because the radius of fluorine is very, very small. And the fact that fluorine is very small, the electrons are very close to the nucleus. It means the nuclear charge is very big. It means the electrons are really, really attracted to the nucleus. So that is the next 2 trends that we know about the elements because of the periodic table. So far, I hope no one's get confused, but those are all the trends so far. Now let's talk about the last trend that we have. Or in this situation, noble gases are disregarded simply because the noble gases are already filled. They do not want electrons anymore because their shell is fully filled. And also, remember, for the radius after fluorine, the noble gases suddenly becomes a lot more bigger because they're just much more stable. They do not need they're basically stable on their own. They do not have any electron affinity or electron negativity. So noble gases for electron affinity and electron negativity are usually disregarded. Okay, but let's talk about the last trend that we have called the metallic and non-metallic character. Metallic character basically refers to the level of reactivity, more specifically of a metal, because metal tends to lose its electron. If you remember, sodium is actually metal and it wants to lose an electron, and that's what we call a metallic character. So when we have a metal in the chemical reaction, this metal usually wants to donate their electron, wants to lose their electron for them to become more stable. And then we have also non-metallic character, which usually refers to the reactivity of non-metals, which for non-metals, they want to receive an electron. They want to gain an electron for them to be much more stable. Again, more specific, a specific example is chlorine. Chlorine belongs to the group G7A, which means it has 7 electrons in its outermost shell, which means it needs one more electron for the shell to be fully filled. So if we have our NaCl, sodium is metallic, it donates its so it readily donates its electron to be stable and donated to Cl, making Cl more negative, fulfilling its shell, making its shell full. So this is an example of non-metallic character. They readily gain an electron. And this is the trend for metallic characters and non-metallic characters. So elements that go from left to right and top to bottom has a tendency to gain an electron, while for elements that go from right to left and top to bottom, they have a tendency to donate their electron. So all in all, the summary of the periodic trend or periodic variation is here. So the ionization energy goes higher, going from left to right and up to bottom. So the ionization energy increases towards this way. Again, higher any ionization energy, it means the more difficult it is for the electron to donate its, or the more difficult it is for the atom to donate its electron, which then makes sense for the electron affinity to also go this way. Electron affinity is the tendency to what? The opposite of ionization energy. It's the affinity of the atom to gain an electron. So the higher you go and the more right you go to the table of elements, those elements right here wants to usually gain an electron, which also makes sense why our non-metallic character is going this way. And lastly, our electronegativity is also going this way. And lastly, the trend that we know is non-metallic characters, which usually go this way, which is the tendency to donate their electron. And that makes sense for the atomic radius to also go this way, because the higher or the bigger the element are, the more readily they can donate their electrons, because the electrons are so far from their nucleus. So the nuclear charge is much more smaller. So those are the various trends that we can actually find in the table of elements. I hope you guys were not confused. If there's anything that is confusing or that is not clear, please do not hesitate to message me. Thank you so much, guys, and may you guys have a great day.